Hi, my name is Sam Cusimano, and welcome to Electricity for Progress. Today we will be exploring Arduino through a part of my Circuit Basics series, where we look at very simple circuits using electronic components like LEDs and resistors, as well as an Arduino UNO, in order to run simple programs, learn how programming works, and learn how to interact with electronic components on a solderless breadboard. I will be using the program Tinkercad offered by Autodesk today in order to simulate an Arduino UNO circuit board as well as a solderless breadboard. I will have linked below all four of the separate Tinkercad coding session circuits that I have set up here as we work through the four stages of this particular installation of Circuit Basics. To begin, we're going to simply set up two LEDs on a solderless breadboard. Here in Tinkercad, you can see on the left-hand side an image of an Arduino UNO. You can see above it there is a USB cable that's not currently plugged in, meaning there is no power attached. You'll see over here a Start Simulation button. Tinkercad allows us to run simulations of both code and hardware circuits. Right now, nothing is running. I have the Arduino board connected from its 5-volt power and ground pins over to this solderless circuit board connected to the positive and ground rails here on the left-hand side of the board. I also have at the bottom of my solderless circuit board jumper wires going, here I have a red wire going from the positive rail bus on the left-hand side over to the positive rail or bus here on the right-hand side of the solderless breadboard. And then I also have a green jumper wire going from the ground bus on the left-hand side of the board over to the ground bus on the right-hand side. You always need to set this up on a circuit board in order to power and ground both sides of the board depending on how your circuit is that you're setting up. For this first step, I only want to verify that my LEDs work. Eventually, we're going to be flashing these LEDs and fading these LEDs, but before I begin with some kind of coding, I want to have a basic circuit that tests to ensure that my components are functional. So here I have two components. One resistor. This resistor is a 220 ohm resistor. We're using it as a current limiting resistor as we power our LED. A current limiting resistor can vary in range between 220, 330, anything below 1000 ohms normally will work. But in this circuit, we're going to make sure that whatever resistor we have, whether it's 220 or some other low value, that we're going to have our LED illuminate. So I'm putting this into the breadboard between, spanning across the two sides, the left and the right-hand side, here in row 10 of the breadboard. Then below, I have an LED, I have a blue LED, and I am plugging that into row 15, again, spanning across the two sides of the solderless breadboard, where the negative pin, the cathode of the LED, is connected on the right-hand side of the circuit board here in row 15, where the longer lead, the positive lead of the LED, or the anode, is connected over here to the left-hand side of the circuit board in row 15. I now have a couple jumper wires that I'm going to set up. This yellow jumper wire that I'm using connects the current limiting resistor to the positive pin of the LED. So I have this jumper wire going between row 10 from the resistor down to row 15 where the positive anode of the LED is plugged in. Next, I want to make sure that there is power attached to the current limiting resistor in order to illuminate the LED. So I have a red jumper wire here going between the positive bus here on the right-hand side of the circuit board into row 10 on the right-hand side of our pins on the circuit board. So now power is going to go in through this bus into the current limiting resistor, down through the yellow jumper wire into the positive pin of the LED, and now finally I'm going to add a green jumper wire that connects between the cathode, the ground pin of the LED, over here to ground. I have a simple circuit that just runs power through a resistor in through the LED back to ground, and this will test and make sure that the resistor that I have that I'm using and the LED that I have actually work. You always need to make sure your components work before building a circuit. Debugging is very hard if you later find that your LED was burnt out or placed in your circuit the wrong direction. So while this may seem like a silly or superfluous step, it's actually vital to make sure that all of your components work, and this is what I do when I'm building a new circuit. Here I'm doing the same thing twice. I have a red LED below, as well I have another 220 ohm current limiting resistor. Again, this can be really any value below 1000 ohms. And I have the same setup with a jumper wire between that resistor here in row 30, going down to row 35 where the positive, the longer lead of my LED, the anode, is connected in row 35 on the left-hand side of the board. I have power going from the power rail here into row 30, connecting into my current limiting resistor, and then back here on row 35, the negative or shorter pin, the cathode of my LED, is connected directly to the ground rail on the right-hand side. Now I'm going to come up here and click the Start Simulation button. This is just like applying power to your circuit. So if you have a solderless breadboard in front of you and your Arduino, you'll just plug in your USB cable, which you will see this will do in a second when I click Start Simulation, and both of our LEDs illuminate. Tinkercad's really cool because it shows you this nice animation of what's going on, and it gives us an environment where we don't need an actual piece of hardware in front of us, but we can still experiment with electronic components that we understand. Here I've tested both of the LEDs illuminate. If I click Stop Simulation, the USB plug unplugs and both LEDs turn off. Again, this is just to test and ensure that both of our current limiting resistors are the correct value, and that both of our LEDs are not only the correct value, but they're plugged in the right orientation. Now, let's explore phase 2 of our introduction to Arduino through our Circuit Basics course. Here, we are actually going to flash 2 LEDs. In the previous example, we set up and tested our LEDs to ensure that they were powered and they're in the correct orientation. And we also made sure that our resistors that are roughly 220 ohms, if they're not that exact value, we've tested them to make sure that it all works together. Here again in Tinkercad, I have my Arduino UNO, and everything is set up very similarly, except for a few changes. Let's zoom in. Here, you can see on the Arduino UNO, attached to pin 12 is a blue jumper wire. Also, attached here to pin 11 is an orange jumper wire. We're going to be using pins 11 and 12 on the Arduino UNO to control these LEDs. I have removed the red jumper wire that we previously had here between the power rail on the right hand side and row 10 connecting into our current limiting resistor. I've removed that jumper and I've replaced that with a blue jumper wire going to pin 12. So now when pin 12 on the Arduino UNO is triggered high, that's going to send a current out through this wire into the current limiting resistor, through our yellow jumper wire down here into our LED and back out to ground. And doing this should allow us to turn our LED on and off using the Arduino UNO. Very similarly below, I have attached a pin 11 here to row 30, where our current limiting resistor here for our red LED is present. And I've removed the red power jumper wire from the power bus here on the right hand side that previously went into row 30. And now when pin 11 is turned high, that should also run current through this limiting resistor, through this yellow jumper wire, into the LED, in through ground, and illuminate the LED. Before we turn the power on here, we need to make sure that our code makes sense. So I'm going to click the code button here in Tinkercad. Tinkercad allows us to use blocks for programming or just the Arduino style C code. Here I'm just using C code because it's a little bit more direct for our lesson. I have a comment up top, blink 2 LEDs in sequence. And what I'm going to be doing here is trying to blink the blue and the red LED. I have at the top of the program 2 variable declarations. Both of them are marked as integers. Here we have LED 1, which is equal to 12, and this will represent pin 12 on the Arduino UNO. And I have an integer for LED 2, which is equal to 11, and that's here pin 11 on the Arduino UNO. And that's set up pretty much above everything else in our code. We have now the setup function where we need to declare how any of our pins are functioning. Here we have pins 11 and 12 acting as outputs to illuminate our LEDs. So I'm setting pin mode here on pin 12 to an output. Ooh, there's a bug in my code. Let me set here pin mode for pin 11 also to output. Next, we're going to go through our loop function. And what I want to do is turn on each LED for 1 second, then turn it off for another second. So I'm looking at, and this is exactly like you would see in the Arduino example sketch for blink. I'm just doing it here with 2 LEDs for fun. You'll see down here we're going to use the digital write function, which will take pin 12, which I'm going to change from a 12 here to now look more like LED 1, which is our variable that we have declared. And I'm going to set that to high, which should turn the LED on. Next, we're going to have a delay, and it says delay 1000. Delay takes in a value of milliseconds, so 1000 milliseconds equals 1 second. We will wait 1 second with this LED 1 set to on. Next, there's a digital write, and I'm going to change that to my variable LED 1, where I'm going to set LED 1 to low, which is effectively the off state. And we're going to again use delay and wait 1000 milliseconds, wait 1 second. Now I'm going to go down here and I want to turn on the red LED, which we're set up to be on pin 11, LED 2. I'm going to change my variable here to say LED 2. I'm going to now make that high, just like above, wait, delay 1 second, and then again I'm going to say LED 2, write it to low for 1 second. So what should happen here, we're going to turn our LED on, wait a second with it on, turn the blue LED off, wait a second, and then again turn on the red LED, wait a second, turn that LED off, wait another second, and it should loop back to the top. And again, running forever, flashing these 2 LEDs. I'm now going to hit the Start Simulation button, which plugs in the power here, runs our code, and you can see the blue LED illuminates for 1 second, turns off. The red LED then illuminates for 1 second and turns off. So now we have a very basic dual LED flasher circuit similar to the other flashers that you may have made using transistors or a 555 timer. Here in lesson 3 of our Arduino Circuits Basics course, we're going to make a small modification to the breadboard setup of our components, but we're going to use the exact same code we just had for our dual LED flasher, where we would set a pin using digital write to high, which would allow current to be sourced through that pin and go into an LED to illuminate it. We would then change our digital write setting to low. Now, when we normally think of a switch turning on and off, we think of a physical connection, where if we have a circuit that's off, there is no connection at all. And when there is a circuit that's on, a switch mechanically closes and allows current to flow through a wire. Now, when we digitally write a pin to high, it's true, current does flow out through pin 12, for instance, and is able to be used by external components. Now, when we set a digital pin to low, instead of it being totally disconnected, instead the pin acts as a sink for current. It is able to act as a ground. And we can use this property to turn our LEDs on and off in a slightly different way. I've modified the circuit where the Arduino UNO is connected to power and ground the same way, and pins 11 and 12 will still be used for triggering the LEDs on our breadboard from the UNO. But you'll see that I have replaced the red jumper wire here from the positive rail or positive bus on the right-hand side of the circuit board over here to row 10. So I'm allowing current, or providing electric current, into the resistor. I've now removed the jumper wire, the green jumper wire I had between the negative rail, the ground bus on the right-hand side, and row 15. And I have replaced the blue jumper wire here going from pin 12. Now it goes to row 15 on the negative side of the LED. Remember, the negative leg is the shorter leg, the cathode of the LED, while the positive lead on the LED is the longer leg known as the anode, which is still connected through that yellow jumper wire into our current limiting resistor. So essentially I've switched. Instead of using a positive pulse of current from pin 12 to illuminate our LED as we did in the last example, here we're going to use the sourcing of current to illuminate our LED. I've left the orange jumper wire from pin 11 here in the same configuration as we had in the previous circuit, where pin 11 will provide a source of current through the current limiting resistor, through the yellow jumper wire into the positive or longer lead of our LED, the anode, down through the shorter lead, the cathode, into the ground bus here on the right-hand side. So in this example, I have the blue LED set up a little bit differently. Our code is exactly the same, where I'm going to digitally write the blue LED high. I'm going to wait a second. I'm going to digitally write it to low, and then wait 1 second, and then we'll do the same thing with the red LED. I'm going to click the Start Simulation button, and you'll notice a very different reaction from the LEDs. Here, we see that the blue LED is on for most of the cycle, while the red LED only periodically flashes for a second. And this is why. When we digitally write pin 12 to high, that effectively turns this LED off, as then we wait for 1 second. When we then digitally write pin 12 to low, that allows current to flow through the blue jumper wire down to pin 12, acting as a source for current, turning on this LED. So the LED is then on for 1 second. Well, that LED is still on because it's in the low state on pin 12, allowing current to sink into it. Then we digitally write pin 11, the red LED, to high, and so it flashes. Then that pin 11 turns low for the rest of the duration of the loop, turning off the red LED. So here the blue and the red LED are essentially doing the opposite thing. Now the blue is off only for 1 second, but it's on for the rest of the duration, while the red LED is on for 1 second and it's off for the rest of the duration. This is an interesting method of controlling different things beyond LEDs, like motors and other transistors, where sourcing current sometimes can be extremely valuable. Now you must be careful with an Arduino or any microcontroller. These can only source or sink a small amount of current, which is one of the reasons that we always include a current limiting resistor in between any microcontroller and our components. And it's also a reason that people often use transistors in order to act as a buffer between an LED or a motor or a high current draw component, allowing the pins on the Arduino or the microcontroller to source or sink only a small amount of current to drive or power down a transistor. In our next segment, we're going to look at a process of fading our LEDs instead of simply having them flash on and off. Now for part 4 of our Arduino Circuit Basics course, we're going to look at fading of LEDs. So just to reiterate through, first we tested our 2 LEDs to make sure that they illuminated, that they were in the right orientation, and that our current limiting resistors were the right value. In phase 2, we made the 2 LEDs flash on and off, back and forth, 1 second each. Then in phase 3, we looked at what happens when you turn a digital pin to low, where current is able to be synced through the pin, acting as a ground, and we changed our schematic a little bit on the breadboard, allowing our pin 12 to be attached to the ground pin of our blue LED. And that produced slightly different results. Now, here in step 4, we are going to revert our schematic back to our normal triggering method using our pins writing high as a source for current, going through our current limiting resistor and then through the positive lead of an LED to ground. But additionally, we're going to add in a potentiometer, which is going to be a knob that we can turn. And that potentiometer is going to be set up as a voltage divider going between ground and positive voltage and running into an analog input on our Arduino UNO. Here we have our same Arduino setup with our 5 volts and ground set up connected to the positive rail and negative ground bus on the left-hand side of our board. On the bottom of our solderless circuit board, we again have the positive red jumper wire between the positive bus on the left-hand side and the positive bus here on the right-hand side of the breadboard. And then we have a green jumper wire to connect the ground between the left and right-hand side of the board. Additionally, you're going to see this potentiometer, and I've placed the potentiometer, which contains 3 pins. One of the pins here, terminal 1, we have connected with a red jumper wire over to the positive rail. And then you'll see the other lead, terminal 3, on the far side of the potentiometer connected through a green jumper wire over to the ground bus. And that leaves us with the middle pin, which is called the wiper. When we plug this pin into our yellow jumper wire, we're going to use that to read a variable voltage between these 2 terminals. Effectively, our potentiometer here acts as a voltage divider from our positive rail to the negative rail, and it will supply a variable amount of voltage here to pin A0 on the Arduino. Looking back at our blue and our red LEDs, again I have attached pin 12 here to row 10, where we normally would have power connected to our current limiting resistor. I now have our ground connected to the cathode, the negative or shorter pin of the LED in row 15 over here to the ground bus. And I have the same circuit set up over here for the red LED. I have this jumper wire. Oh, it's green. Let's change that to orange. I have an orange jumper wire going here to row 30 from pin 11, going through the current limiting resistor. We have a yellow jumper wire coming down here to connect to row 35, where the positive or longer anode of our LED is connected, going out to the cathode. And now I have a green jumper wire connected in row 35 on the right-hand side from the negative pin of the LED to ground. Again, this looks just like our dual flasher example in step 2, with the addition now of a potentiometer. Okay, now let's look at the code. In the code, I've got a little comment at the top. I want to fade an LED, right? Slowly turn it on and off, rather than our digital right, which tends to turn things directly on and off. I want to fade an LED or two when I turn a potentiometer, okay? So I'm going to now start with a couple variables that I'm going to declare at the very top of our code. Here I have an integer, which I'm calling sensor pin, and this sensor pin is what's going to detect the changing voltage coming from our potentiometer. I'm setting that to A0, analog pin 0, here on the Arduino. Some pins are able to read an analog voltage, like A0. You might say, hey, wait, you're setting an integer variable to some weird string with an A and a 0? Yes, in Arduino, the value A0, when you're talking about a pin, is magically mapped in a library in the background to the actual name of the pin in hardware over here on the Arduino UNO. So we can use an integer to set our pin value to A0, the name of that analog input pin on the UNO. Similar to our other examples, I have an integer for LED 1 set to pin 12. I have an integer for LED 2 set to pin 11. And then I have another new value, an integer called sensor value. And this is going to hold that analog value that we read from the potentiometer through pin A0. I'm also going to now utilize a thing called the serial monitor, which allows us to communicate between the Arduino UNO and our computer using USB. Serial information can contain text or numeric strings, all types of different data, but we can utilize that to debug or read what's happening. So now I have a new line in my setup function that says serial.begin 9600. 9600 is the baud rate that we're using to read our values between the board and the computer. Don't worry too much about it, just set it to 9600. And we have our pin mode set for LED 1 as an output, pin mode for LED 2 as an output. Always you should declare what your pins are doing, whether they're an input or an output. Here we don't have a declaration for our sensor pin A0, but by default analog pins are, when they're declared, are set as inputs. You can also be specific or explicit about that in your code. Here we don't need to. All we need to do is suggest we're starting our serial data so we can read our value on through the serial monitor, and we're setting our pins 1 and 2 here, or LEDs 1 and 2, pins 11 and 12 to outputs. When we go into our loop function, I am now assigning the sensor value to a new value using the analog read function. I'm saying analog read through the sensor pin, which maps to A0. So I'm saying take a reading directly out of this analog pin from our variable potentiometer here and set that to sensor value. Now, when we do an analog read, we get a value on the Arduino between 0 and 1023. The range of a value you get on your sensor reading, I'll say on your input, very often is not the same range of values you need for your output. In our case, the output is the fading of an LED. Now, the input of a potentiometer ranges between 0 and 1023, which is really going all the way from one side to ground and all the way to the other side to the positive voltage. But the range for fading an LED is going to be between 0 and 255. 255 is the maximum value that you can utilize for another function we have called analog write. And analog write will allow our LED to slowly fade or turn on to different values depending on the input value, which is limited to 255. In order to accomplish this, I have another line that resets our sensor value. We're going to map. We're going to use a new function called map that translates our incoming value, which is our analog read, from 0 to 1023, right? The large range, to a smaller range. We're mapping down to between 0 and 255. So now our sensor value is going to be within the range of 0 to 255, and it's mapped directly down from how it read in from the analog input. I'm now going to analog write to LED1 our sensor value. So, and then I'm going to write the same thing to LED2. Both LEDs are going to be written with the same analog write value. On certain pins of the Arduino, we're capable of having pulse width modulation output. You'll see these squiggly lines next to pins 11 and 10, 9, 5, and 3. That means that these pins are actively able to perform a type of fading. Now, you'll notice we're connected to pin 12 here, which is a digital pin, and there is no little tilde next to it. Well, let's see what happens when we run our code. I click Start Simulation, and both of the LEDs are lit. Now I'm going to grab the knob here, and I'm going to start to turn it. And as I turn the knob down, you can see the blue LED and the red LED seem to fade, but there's a big difference. Here, let me start from the other side. The red LED and the blue LED are now both off. As I slowly move the knob up, you'll see the red LED illuminate. And then as I move the knob up a little bit more, you see the red LED, it continues to glow a little bit brighter. But the blue one up here is still totally off. Now as I move the potentiometer to the middle range, again, the red LED is brighter. As I move the knob up a little bit further, oh wow! Now the LED on the red side's a little bit brighter than it just was at halfway, but the blue one is fully on. Okay, this is the difference between a digital and an analog or pulse width modulating pin. Pin 11 is capable of giving us a nice smooth fade of values from 0 to 255, allowing our red LED to fade in and out nice and smoothly. The digital write on pin 12, on the other hand, forces this only to turn on and off, and when we get past 2/3 of the voltage, boom, that digital write pin is going to turn on in full. This example is meant to show you not only analog changes, analog reads on the LED, and analog outputs to fade, but the difference between an analog output here in pin 11 on the red LED and a digital output here on pin 12 that just simply turns on and off. Now I know on Tinkercad in the simulation it looks a little bit like this blue LED is fading, but trust me, try it on your hardware and you will definitely see that the blue LED only turns on and off at certain times. Oh, And what about this serial print line? Well, also included in the Arduino IDE is a serial monitor. So you see this value 20. This value 20 represents the value that's being written to the LEDs. So as I turn the knob, you'll see that value go up. Here I'm halfway, and I keep going up all the way to the top, and it maxes out at 255. Because again, we're using the map function here to take our analog reading, which normally would be between 0 and 1023, bringing it down to 0 and 255, and that's what's writing to our LEDs. So this example combines our serial monitor, allowing us to track the actual value that's coming out of our not only potentiometer, but also our mapping function, and as well as showing you the difference between a digital and an analog writing pin. I hope that you have been able to follow through all 4 of these lessons as we've built up from our basic test example into a dual LED flasher, then looking at what happens when you drive a pin to low, because you can still turn on an LED with the right circuit when a pin is low. And then finally looking at how we can fade LEDs, the difference between our analog and our digital pins, and then a quick reference here to our serial monitor, allowing us to read values for the different sensors and variables that are in our project. Thank you very much for following through, and go back to earlier parts in this lesson if you need to get different results. There's at the top of each of the code bases a couple experiments you can try. Here I suggest switching from pin 12 to pin 10, which will allow both of the LEDs to fade smoothly in and out. You'll also need to change the code in order for that to work. Good luck and happy coding.